we were talking about, or beginning to talk about the following theorem, so, which I will restate. So, given mu from omega into the complex numbers, mod u is less than or equal to, say, lambda, which is less than 1, almost everywhere, then there exists p, which is bigger than 2, which is close to 2. So this is the theorem that we were starting to talk about at the end of yesterday, the end of Wednesday. I'm going to state it in a less sloppy way this time. Thank you to Josh for discussion at the end about this. So, given mu, the complex numbers, whose absolute value is strictly less than 1, less than lambda, which is less than 1 almost everywhere, there exists some p bigger than 2, but it's going to be close to 2, close depending on this number lambda here, such that if we have some phi belonging to LP, complex numbers into the complex numbers, we can find f that solves the following Beltrami type equation, that df by dz bar is equal to mu df by dz plus this guy like this. Okay. Later in applications, we're going to take this guy phi just to be mu itself on the set omega and 0 outside, and that's how we're going to get the solution to the Beltrami equation that we've been building up to. But such a function would clearly belong to LP for any p at all, actually, because this is an L infinity bounded function. Okay, but to begin with, we solve this guy. So, proof, we're going to use the machinery that we've built up. So, we're going to define f to be this Cauchy type transform P, composed with 1 minus mu of S being the Beurling transform, minus 1, I'll explain in a second again what this is. This is the identity here, this times phi, like this. Okay, so this makes sense. Because the operator, let's call it G, going to mu times the Beurling transform of G, is, or has, LP norm less than 1, because if we take the LP norm of mu of S of G, it is less than or equal to the L infinity norm of mu times the LP norm of Cauchy transform, which we'll denote by CP, or at least, let's denote it by CP, and then this thing. So recall, we're assuming that the Beurling transform is an LP bounded operator, and that its norm is given by CP, and CP tends towards 1 as P tends towards 2. So actually, let me complete this inequality. So that's less than or equal to this lambda times CP times LP. So recall, as what we assume S is LP bounded, and LP bounded operator with norm CP, and then limit as p goes to 2, Cp equals 1. This is our assumption. We're later going to prove that, and that's going to be a non-trivial thing indeed. That's going to use theory of singular integral operators. But just assuming this for the time being, we're going to show how we can solve the Beltrami equation. Okay, so if this is the case, then we are happy because Cp is arbitrarily close to 1, right? Lambda is strictly less than 1, so we can choose p sufficiently small to make this number right here strictly less than 1. Right? Let's call this thing just to omega, which was lambda times Cp, is less than 1. Okay, that's what we talked about on Monday. And then this makes us very happy because we define one minus mu of s to the minus 1 to be this thing, to be the sum from k equals 0 to infinity of the operator of the Beurling transform applied to the function multiplied by this function mu on the right-hand side, that operator taken to the power k. Okay, yeah. And we learned, and with this definition, that well, when we apply this operator to an LP function, then we do get something in LP out at the end just by summing up the contribution of these norms, right? So let's give ourselves another function. No, let's just stick with the same one. So this thing, let's put the LP norms around this, is less than equal to some k equals 0 to infinity of the LP norm of this thing, phi LP, which is less than the sum k equals 0 to infinity, and then this omega to the power k times phi to the LP, and this is a finite sum, so this is, well, we know what it is because we do calculus, so it's this. Yeah. So in other words, we're later going to show that this is a linear operator and good stuff happens for this guy, but simply defining this thing like this, yeah, then when we plug in some phi into this expression, we do indeed end up with an LP function. So we can apply the Cauchy type transform to it, and it's a meaningful thing because we learned about the fact that Cauchy transform maps functions in LP to hold a space, and everything is cool. Yeah. So this is at least at this stage we know at least this is a meaningful thing. Yeah? Yeah? But I'm further going to show that this thing is a linear operator, which is not hard to see. So I'm gonna write op dot for operator to save writing, and it's actually as the way it's written suggests, this thing is actually inverse of this thing. Yeah, we're going to show that this is true. Okay, which is slightly non-trivial, but we'll see that it is actually the case. Okay. So that's what we're going to do that's what we're going to show about this guy. But before I could do that, I want to show that if you believe that, If that is true, then we can rather easily get a solution to this Beltrami type equation. Okay? So that's what I'm going to do on the next board. We're going to use our differential relations that we learned about the Cauchy type transform and the Beurling transform to actually solve this under this assumption. Okay? So remember this, and we'll use it shortly. Any questions before I erase? Everybody happy? Everybody happy? Good. Let's erase. So, assuming to be proved that G going to 1 minus E of S minus 1G is linear and inverts 1 minus mu of S, like on the left-hand side. Then for F, which recall was the Cauchy type transform of this operator 1 minus mu of S to minus 1, applied to our LP function, we have the following. Firstly, if we take the conformal part of gradient so we're doing this in the weak sense because that's all we can do at the moment. We just know it's an LP function, right? So assuming we do this, then in the weak sense, then this is equal to this. But we learned from the previous class that in the weak sense, when we take the conformal part of the gradient of the Cauchy transform of an LP function, then that is just the same as the Beurling transform of this guy. Yep, that's what we learned. Okay. So let's say weakly. So let's call it W be this function, 1 minus mu of S to the minus 1 of phi, which is just an LP function as far as we know. Okay. So let's write that again. df by dz is equal to S of W then. Yeah? And if we take the anticonformal part of gradient like this, then this is the anticonformal part of the gradient of this guy again. Let's call it W straight away this time. Yeah? And we know that this thing, again weakly, just gives us back the identity. That's the other thing that we learned. So then this is just W itself. Yeah? And let's write W as let's write W as W minus mu of S of W plus mu of S of W, which is obviously true. Again, S of W makes sense because W is an LP, so this is a meaningful expression. Then this is the same as, let's differentiate lines a little bit, as the operator 1 minus mu of S applied to W. Yeah? That's the same as this. And then mu of S of W is the conformal part of the gradient of F, like this. Yeah? So, 1 minus mu of S of W, by definition of W, where did I define it? Here it is. This is 1 minus S of W. So actually I meant to say the inverse on the right, not the left. Like this, yeah, times W, times phi, like this, which gives us back phi itself. Yeah? So if this thing is true, that this guy is a linear mapping and we can do this stuff and we actually have a inverse on the right, then this guy turns into phi, and then that's exactly the equation that we have, or that we want. Thus, let's call this thing star. Becomes df by dz bar is equal to mu df by dz plus phi. We are in good shape. What I should have added is that mu, which I initially defined just on omega, we're going to extend by 0 outside of omega, so that when we take s of some LP function times mu, then that mu has to be defined for all z, otherwise that operator doesn't make sense for all z, and mu has to be extended by 0 outside. Okay, so where throughout we actually only going to care about mu is considered the 0 outside of omega. Okay, so phi is our initial guy, which is LP, right? So when we do this guy, we just get an LP function, right? When we do the Cauchy type transform, we just end up with something holder, which comes out from this. You know? So we don't have pointwise gradients. But as a corollary to these identities that we proved last time, we do have that the conformal part of the gradient of f is this thing, which is a well-defined function, okay? Which is a well-defined function because we know this thing is LP. Yeah? So we know that f actually has a weak derivative, weak conformal derivative. And from the other identity, which is this thing, we have that f has a weakly and anti-conformal part of gradient, yeah, because w itself, again, is an LP. So f is implicitly a Sobolev function, which I think, or at least I hope I mentioned, as a consequence of these identities. Yeah? So this is now considered as an LP function. These are weak derivatives, these are not pointwise derivatives. Okay. Where df by dz and df by dz bar are weak derivatives. Thank you very much. Yeah, thank you. Okay, cool. So is everybody happy? Yeah? So later we're going to take phi to be just equal to mu on omega, or just mu, considering omega to be extended. Then G, which will be f of z plus z, will actually solve the Beltrami equation we've been working hard towards. I mean, actually, we can just check that now if we want. I'll just say it briefly in words. Because if we take the conformal part of the anticonformal part of the gradient of G, it's just going to be anticonformal part of the gradient of F, because this thing will just vanish. Yeah? And the conformal part of the gradient of G will be conformal part of gradient of F plus 1. Yeah? Yeah? So that means that we could factor out this mu when phi is equal to mu, and we'll get exactly the identity that we want. Yeah? but we'll get to that later. Our task now is to show that this thing makes sense, that we can actually treat this guy like it's inverting this thing on the right-hand side, for this step to make sense. And once we do that, then our equation is solved. We should also use the fact it's linear, because we're probably using it implicitly, and it's not hard to show. So let's underline that thing. So we need to show star. Okay, so firstly, let's recall how it's defined. It's defined like this. Here's the sum from k equals 0 to infinity of mu of s to the k like this. Yeah, that's how it's defined. Yeah. And then what is that? I mean, this only makes sense as the limit as capital N goes to infinity. Well, actually put that on a different line. So if we take any LP function, let's just call it h, then this is defined to be the limit as capital N goes to infinity of this thing, of the sum from k equals 0 to infinity of mu of s to the k times h. We had an estimate to show that that was an LP. We actually don't know at this point yet if this makes sense, right? We don't know if this limit, oops, this should be up to n, if this limit even exists. But the same estimates make that not too hard. So notice that for any n1, n2, let's take n1 less than n2, then if we form the Cauchy sequence of this partial sum from k equals 0 up to n1 and k equals 0 up to n2, and then take the difference of those guys, then we have the following. Sum k equals 0 to n1 of mu of s of k times h minus the sum from k equals 0 to n2 of mu of s of k times h in the LP norm. This is equal to, I can do less than equal to straight away, less than equal to the sum from k is equal to n1 to n2 of the LP norm of mu of s to the k times h LP, and then this is stuff that we've already seen, sort of k equals 1 to n1 n2 of omega to the k, and let's factor out the HP norm, the LP norm of h LP, like this, yeah? And then since omega is less than 1, then this is forming a Cauchy sequence as n1 and n2 goes to infinity, and therefore this sequence of functions, yeah, it forms a Cauchy sequence in the Spanx space, and therefore it does have a limit. It's a well-defined thing. So this is a well-defined thing, yeah? I should probably have started with that. Yeah, cool. All right, so it's well-defined. I'm going to raise the board. Yeah, I'm going to raise the board, and while I do that, try and figure out why it's linear. Try and figure out why it's linear. And if you can do that, then try and figure out why it inverts this guy. Okay, why is it linear? Yeah, just by the limit laws, right? So So okay, and both of these limits exist, as we've just seen. Therefore, the sum of these limits the limit of this sum is the sum of the limits. So this is equal to, let me just write it, mu, 1 minus mu of s to the minus 1 of h1 plus 1 minus mu of s to the minus 1 of h2, and therefore that's it, that's the claim. Yeah? And exactly the same if we multiply this thing by some lambda, we can pull the lambda out in exactly the same way. So this is a nice linear operator. Yeah? Cool. So that thing, so linear. And like this. Now, if we take 1 minus mu of s times 1 minus mu of s to the minus 1 times h, then what's that? That is, let's put it here, 1 minus mu of s, and then this is the limit as n goes to infinity of the sum from k equals 0 to n of mu of s to the k times this function h, like this. Yeah? And then this limit exists in the sense of LP, right? So the difference between the nth partial sum and the actual infinite sum tends to 0 in LP norm. That's what we just showed, right? Because we have this tail estimate of the final parts of the sum. Yeah? Thumbs up if you believe me about that. Okay, cool. So that is cool. And this operator, mu times s, is a continuous operator in LP. That's our assumption, and so is the identity. Yeah? So we can pass this limit out from this thing right here. Yeah? We can take the limit through this operator because it's a continuous operator in LP. So this is the limit as n goes to infinity of 1 minus mu of s, and then this sum, 0 to n of mu of s to the k times h, like this. And then we just look at what that thing actually is. Limit as n goes to infinity. And the identity will just give us that this is the sum from k equals 0 to n of mu of s to the k times h. And then minus, when we take this guy through, then we're composing this operator with yet another mu times s, right? So then that's the same as the sum k equals 0 to n of mu s to the k plus 1 times h, or applied to h itself. Yeah? And then it's like this truncating, telescoping series stuff we do in calculus. We'll have a whole bunch of terms we'll cancel. The only thing that will survive will be when k equals 0 and when k is equal to n in this thing right here. So this will just be the limit as n goes to infinity of h minus mu of s to the capital N plus 1 applied to h. Yeah? But as we've seen, the LP norm of mu of n plus 1, oops, applied to h, LP, is less than or equal to omega n plus 1 times the HP norm, the LP norm of H, which tends to 0 as n goes to infinity, right? So this limit right here in the LP sense is going to be just the function H. Yeah? That's what this says. Yeah? So is just equal to H itself, and that's the claim. So I thus, let's call this thing star. Star is equal to H, and claim is proved. Or prove N. Cool. Everybody happy? Yeah? Speak up if you're not happy. Okay. So, again, all of this is under the assumption that we have that the Beurling transform is bounded in LP, and that the LP norm is such that when we tend P towards 2, then the LP norm tends towards 1. Okay? All that stuff is underlying this, but this does now give us a complete proof of the thing we claimed. No? So let's see how this actually gives us the principal solution of the Beltrami equation. So, take phi to be equal to mu i.e. I of z is equal to mu of z for z inside our region omega, and it's 0 outside. Which I implicitly assume that's what mu is, but I'm going to write it down explicitly because it's important now. It's very important. So, then, let g of z, or first let's take a solution f that solves this Beltrami equation that we want. Df by dz bar is equal to mu df by dz plus mu. Yeah? Where mu again is assumed to be extended by 0 outside of omega. And take, I don't know where to restart that, maybe here, take g of z to be equal to f of z plus z. Then dg by dz, z is df by dz, z plus 1 itself, yeah? And dg by dz bar of z, well, this z will just cancel, will just vanish when we take the anticonform part of the gradient, right? Df by dz bar, like this, yeah? And then this equation here can also be written as mu of df by dz plus 1, like this, yeah? Like this, yeah? Let's call that star star. So continuing down here. So this is not good board management. Thus, we have that dg by dz bar, oops, is equal to mu g by dz, yeah, on the entire complex plane. And again, these derivatives just hold in the sense of, these derivatives are just LP functions, so this holds almost everywhere. Actually, maybe I should say this, almost everywhere on G. Because these are just LP functions, yeah? And that's exactly the Beltrami equation that we want. And further notice that and if Z does not belong to omega, then from our initial equation right here, if Z not inside omega, then mu of those Z's are just 0, right? Which says that the anticonformal part of the gradient is therefore 0. The F by the Z bar at Z is equal to 0, i.e. F is holomorphic on the entire complex plane, take away our set omega, like this. Yeah? That's what we know. Yeah? Everybody happy? Now to show the principal solution, what we're going to do is we're going to show that as Z goes out towards infinity, then this F is going to be increasingly negligible in the sense that the gradient of F is going to decay like 1 over mod Z. So as we go out towards infinity, this is looking more and more just like the identity function. Yeah? So this G that we find, so let me put a little picture here. So we have our region omega, whatever it is, okay? And we have some prescribed Beltrami coefficient on omega, okay? We find some G that will solve this equation inside omega here. Yeah? And as we go away from omega, then G is going to flatten out more and more and just look like the identity function. Yeah? So this is the image, and then this will be transformed into whatever. This is, say, G of omega. But as we go outwards, then G is continued to be defined, and it's just going to be more and more like the identity. Okay? So we have this distortion of the plane happening with the exact Beltrami coefficient that we want, and then G sorts itself out and flattens out towards just being the identity towards infinity. And we need that because in the Stoilov decomposition, one of the key things was that we could find, well, the key thing was that we can find a quasi-conformal mapping with the same Beltrami coefficient as some arbitrary quasi-regular mapping. Yeah, that's how it worked. So the quasi-conformal, the Beltrami coefficient is the one we inherit from the quasi-regular mapping we are given in the hypothesis. We then find our quasi-conformal mapping via G, and the reason it's quasi-conformal is because its determinant is always going to be positive, or almost ever going to be positive, because it solves the Beltrami equation on the set omega, and mu is strictly less than 1, right? So the anticonformal part of the gradient is strictly smaller than the conformal part of the gradient, yeah? So therefore determinant is strictly bigger than 0 everywhere on omega, yeah? And outside of omega, it's conformal, it's holomorphic, and therefore again the determinant is strictly bigger than 0, yeah? Except where there might be some poles, but there are no poles, except where there might be some zeros of the gradient, but there are no zeros of the gradient, because as we go out towards infinity, it's more and more that the thing is flattening out and looking just like the identity function. Yeah, because this part here the gradient of G is the gradient of this guy, and then this guy, and we'll show the gradient of F is decaying like 1 over mod Z. Okay. So some of you, well, perhaps only a few of you, know a bit of degree theory, and having something which is invertible on the, having something which flattens out more and more like the identity on some region whose determinant is positive almost everywhere, means that you can invert it, because the only way that could not happen is if you have actual things that fold across each other. So what I mean is the following. Imagine you have some rubber sheet, okay, where it's fixed to be the identity around the outside, you know? And then you can do some distortion to the rubber sheet, you know? But you're not allowed to have that the rubber sheet has got negative determinant, which would mean reversing your orientation. Yeah? Then when you distort the rubber sheet, that means you can't put folds on top of it. You can't take part of the rubber sheet and fold it on top of itself. Because if you did, then you'd have a negative derivative. Yeah? And the derivative would be negative. So therefore, the only kind of distortion you can do is just like squishing it around, like pulling it around. But all of those kind of distortions are reversible. It's still going to be a one-to-one mapping. That's degree theory in a metaphor. Yeah? If you don't know degree theory, it doesn't matter. I will try and convince you of this a bit later. But that's why we care about this. That's why we're going to make efforts to control the gradient of F and to show it goes more and more down towards 0 as we go towards infinity, so that on the grand scale, G is looking more and more like the identity, and therefore G will be an invertible mapping, and that's what we really require for G. That's the whole point of this, is to find a quasi-conformal mapping that has the same Beltrami coefficient as a given quasi-regular mapping. Is that making some sense to you guys? That's why I want to take G, well, F doesn't solve the Beltrami equation I want, right? It solves this thing, whereas G solves... Yeah, but all of these things, all of these moves are done in the entire complex plane. So, oh, I see. I guess I see what you're saying. So you're saying that I know that this is true inside omega, and I could just say, okay, I don't care outside omega. I'll just take this guy to be the solution, and then outside omega, let's just call it 0. Yeah, but that's no use for us, because we need to use the fact that it is a non-zero mapping that looks more and more like the identity as we go out towards infinity to prove invertibility. We are going to use things we know about F to show. Let me just write down what we're going to show, and then you guys can think about it. So we will show in the next class that df by dz, so there is only a conformal part of the gradient when we are outside of omega because of this thing. So df by dz of z is less than some constant over mod z as z goes towards infinity, like this. Okay? That's what we're going to do. And to do that, we're going to use the fact that F is holomorphic outside of this guy. Okay? And we're going to use that F is actually a bounded function, because it's a bounded function on any bounded region, because F is what we get from doing this Cauchy type transform on an LP function, right? So looks like F is no longer here, but F was the Cauchy type transform of this guy, oops, 1 minus mu of s, so minus 1 like this, of our function mu, the extended function mu, yeah? Where mu is considered to be 0 outside of omega. Yeah? So this is an LP function, so P of this LP function is a Holder continuous function, so then this thing is bounded on omega itself, and let's take some ball containing omega. It's bounded on that ball too. Yeah, so F is holder. Okay. So using that fact that it's bounded on omega, or any ball containing omega, any finite ball containing omega, and the fact that it's holomorphic, we are going to do these estimates, and what should come to mind is Cauchy integral formula for derivatives, which has this kind of thing. Yeah? So that's a hint. That's a hint as to why this works. So think about how we can prove this using these components for Friday, and then we'll complete the proof of this on Friday. Cool. All right, everybody happy? Well, no final questions? All right, so see you all on Friday. Have a great day.